So the graphical representation of SHM, we have the graphical representation for the SHM for the particle starting from the mean position and the extreme position. Here we'll calculate the total maximum minimum displacement, maximum minimum velocity, maximum minimum acceleration. With respect to that, we have the graphs for the displacement, velocity, acceleration when the particles goes from the mean position to the extreme position. So at the mean position, when the time equals to 0, we have alpha equals to 0. So x, we have the equation x equals to a sine omega t plus alpha. Substituting the values, we get the displacement equals to 0. So when the particle starts from the minimum position, the displacement is first 0. At the extreme position, when t equals to 0, the displacement is maximum. So substituting the values, we get alpha is equals to maximum, that is pi by 2 or 3 pi by 2. Substituting the values, we get x equals to a sine 3 pi by 2, which will gives you minus a, that is the maximum displacement when the particle starts from the extreme position. Next, for the velocity, we have maximum minimum velocity when the x equals to 0. We substitute in the velocity equation, we get velocity is equals to a omega, that is the maximum velocity when the particle starts from the mean position. Next, velocity for the extreme position, x becomes equals to plus minus a when the particle starting from the extreme position. We substitute the values, we get velocity equals to 0. So velocity is equals to 0 when the particle starts from the extreme position. Again, for the acceleration, we have x equals to 0. Acceleration becomes minus omega square 0, that becomes equals to 0. So acceleration is 0 when the particle starts from the mean position. Next, again, acceleration will be maximum. Acceleration will be maximum when x equals to plus minus a. So acceleration will be maximum when the particle starts from the extreme position. Next, here we have composition of two SHMs, that is we have two waves which are superimposed on each other. We have the two wave equations x1 and x2, x1 and x2. x1 equals to a1 sine omega t plus alpha 1, x2 equals to a2 sine omega t plus alpha 2. Now the analytical treatment for the composition of these two waves is we add these two waves x1 plus x2, and the resultant we get is x which is equals to x which is equals to r sine omega t plus delta, well the value of r will be different for sine delta and cos delta. Now we'll find the value of r, that is the resultant amplitude, and the delta, that is the phase angle, which is delta. So we square and add these two equations. Squaring and adding the two equations gives you r equals to a1 square plus a2 under root a1 square plus a2 square plus 2a1 a2 cos of alpha 1 minus alpha 2. Then again we divide square and divide the two equations. We get the tan inverse alpha 1 sin alpha 1 a2 a1 sin alpha 1 plus a2 sin alpha 2 upon a2 sin a2 cos alpha 1 plus a2 cos alpha 2 equals to the del, that is the phase angle, and the r resultant amplitude we can find out by treating these two equations, adding and squaring and adding and dividing again. So we get the equations for the resultant amplitude and the angle difference. Then we have the maximum we have the motion for the simple pendulum. As we all know, for a simple pendulum the time period is equals to 2 pi under root L by G, where L is the length of the string and G will be the gravitational constant.